Good evening, buenas noches, and thank you for tuning in. On behalf of all of us at the locally based, independently owned bookstore Books and Books in Miami, Florida, and in partnership with Miami Book Fair, it's my pleasure to welcome you to a virtual evening with Amy Webb and Andrew Hessel to discuss The Genesis Machine, our quest to rewrite life in the age of synthetic biology, published by our friends at Public Affairs. Amy Webb is a quantitative futurist, founder of the Future Today Institute, and award-winning author of The Big Nine and The Signals Are Talking. She writes extensively about biotechnology, artificial intelligence, technology policy, and business strategy, regularly contributing to publications including Harvard Business Review, The New York Times, Wired, Fortune, Mother Jones, and others. Her TED Talk has received more than 8 million views. Andrew Hessel is a microbiologist and geneticist who has worked on the leading edge of genomics, bioinformatics, and synthetic biology. He is the co-founder of Humane Genomics, Inc., a seed-stage company developing virus-based therapies for cancer. He is a co-founder of the Genome Project Right, the international scientific effort working to engineer large genomes, including the human genome. His goal is to help people better understand and use living systems to meet the needs of society. Just a quick reminder that throughout this evening's broadcast, you can post questions below in the Ask a Question feature at the bottom of the screen. And please order your copy of The Genesis Machine from Books and Books and support independent bookstores. And now, without further ado, I'd like to welcome our guests to the virtual stage. Hello.
Hey there,
Hi.
how are you? Hey, Andrew.
Hey, Amy. How you doing?
How are you?
Hi, everyone.
Hey, everybody. Thank you so much for being here with us live. And if you are watching this after the fact, thank you for being with us on demand. We really appreciate it. And we so appreciate Books and Books. We love independent booksellers, and we're just really excited and happy to have this opportunity to share our work with you tonight. We have a little bit of an overview conversation planned, and then we really look forward to taking your questions. Before I hop into the overview, Andrew, is there anything you want to say?
No, just delighted to be speaking with you this evening.
Yeah.
Let's get it going.
Yeah. And I should note, Andrew and I are bi-coastal right now. So Andrew's on the West Coast, and I am on the East Coast. And again, we're just happy to be here. So why are we here? We wrote a book called The Genesis Machine. And the book is about an emerging technology that's going to allow us to edit, redesign, and create new forms of life. This is going to give us options to deal with existential threats like climate change and novel pathogens. But it's also going to give us an opportunity to improve human longevity. You're not hearing a lot about this new technology yet because it's relatively new. And we're just starting to see use cases in the marketplace. So as you hear us talk about our work tonight and all of the research that we did, bear in mind that this is a very long horizon technology. What's exciting is that we're all here right now watching this new generation being born. It's really exciting. Now, there are enormous opportunities ahead, but there are also some risks. And the first has to do with the fact that we don't have a global consensus yet on how to make decisions that could benefit or potentially harm us on a planetary scale. In the United States, our regulatory frameworks are woefully inadequate, which creates a strategic vulnerability. And in some cases, our regulations help invention and innovation, and in other cases, it hampers it. We're also drastically underfunded in key areas of science, including the one that we cover in the book. There really hasn't been any consistent government funding for basic research. So it tends to be done in the private sector, which is fine, except that typically when you get outside investment, those investors expect a return. And that can create a challenging situation for the researchers who are heads down trying to build out and test and design all of this new biotech. And eventually there are some potential challenges, which you undoubtedly will ask us questions about. We get these questions all the time. And that has to do with human enhancement and what's on the horizon, what's realistic, what can and should be allowed, and whether or not this leads to a new type of genetic divide, one in which some people are enhanced and in other cases, people are not enhanced. So the technology that we cover in this book, Andrew's going to explain in more detail, but it's called synthetic biology. The promise is that if we can develop our thinking on synthetic biology today, if we can meet each other in the middle, acknowledge the risks while keeping ourselves abreast of the opportunities, then, and if we can also have some difficult conversations that we will necessarily need to have, we're going to be much closer to solutions for existential challenges like global food insecurity, water shortages, extreme weather events, and plummeting biodiversity. The book that we've written is about science, but it is not a science book. It's actually a book about people. It's a book about people and their stories. It's about me and my personal stories, and it's about Andrew and what he's been through. To some degree, it's about our struggles to start families, but it's also how we used technology to create the families that we wanted to have. The book is about the scientists who had to break free from the establishment to invent new technologies, CEOs who had to learn very hard lessons about trying to make money to monetize synthetic biology too quickly, presidents of various countries, including former President Donald Trump, whose DNA could make them a security risk. This book is about us, but it's also about you and your life and the decisions that you are going to need to make in your lifetime. And those decisions have consequences. So Andrew, maybe you might tell everybody what this synthetic biology stuff is and how it works and how you got excited about it and involved in it.
Okay, I'll try and keep this accessible. First of all, the name synthetic biology is a misnomer. This is biology. It's not synthetic in that it's in any way artificial. It is at the core, it is genetic engineering done with a better set of tools. And so the overarching aim is to make genetic engineering and life science in general easier to engineer. So what does that look like? Well, 30 years ago, doing genetic engineering required laboratories that are essentially complicated kitchens. It requires using specialized equipment. It requires having specialized training and specialized reagents, ultimately to take the DNA molecule and to edit it the same way we used to edit films, by physically cutting the film, in this case, cutting the DNA molecule and splicing it together to make new edits. This, you can imagine, is difficult to do because you're working with a molecule. It's not something you can see. Synthetic biology started to bring the same tools that we started to see in music editing and film editing to the genetic world, allowing us to sit down at a computer screen, work with digital DNA that has come off of the DNA sequencers, machines that read DNA code and put it into computer files, and allow us to do the manipulation of the digital DNA using software tools. The important and revolutionary part of synthetic biology, though, is that there is a printer that has been developed to print the DNA molecule. So once the programming or editing of the DNA molecule has been completed, we can now print out a new DNA molecule which essentially works as the program that a living cell can run. Now, like any digital technology, it starts relatively simple, relatively straightforward, and it grows faster, better, cheaper as we build better tools. So synthetic biology is not new. We've been synthesizing DNA for many decades, but the programs, the length of the DNA molecule we could write, which is loosely equivalent to the complexity of the program, was pretty small. So we could, about 20 years ago, we started to be able to write protein-sized molecules, which has advanced everything from therapeutic development to the development of enzymes that are in your laundry detergent. More recently, we've been able to start writing complete genomes of microbes, both viruses and bacteria. And meanwhile, the software tools for doing the editing work and the design work, the printers for printing out new DNA code, the sequencers that allow us to read nature's code and put it into the databases, and ultimately the robots for doing test and measurement of the reprogrammed organisms have all been getting faster, better, and cheaper. So the short version is my generation started to program computers. Now my kids and your kids are going to start being able to program living organisms in much the same way, sitting down in front of digital tools, working with colleagues online, and doing things that if we were to do it in a lab 20 years ago would have been impossible.
Now, Andrew, I'm sure that there are people listening to us who are currently thinking like, all of this sounds made up. This sounds like complete science fiction. But you've had some experience to, this isn't made up stuff. This is very much happening, right?
Yeah, so I've been watching it unfold. In the 1980s, I was one of the first people to come along and start working in an emerging area called bioinformatics, which was really just starting to take genetic information that was coming off of sequencers and putting them in computer files and doing this type of analysis, not even editing, like just learning, what does this string of genetic code mean? What does it do? So I loved it. I ate it up. So I was in academia working on microbes, and I was lucky. I ended up getting scooped up by a biotech company that was writing short programs to make hormone drugs that told blood cells to grow, red blood cells and white blood cells. So I was able to transition very early from academia to industry and see these technologies be applied and do amazing things to help people that were sick. But along the way, I realized, wow, this stuff is going to get faster, better, cheaper because of the digitization. And so I started to specialize more and more, not in reading and analysis, but in writing. And so I started to chase down groups that were developing synthesizer technology, DNA synthesizer technology, that were starting to write programs from scratch to reprogram cells. And it's just been a fascinating ride. My last company that I founded was based on writing small genomes from scratch. So we wrote viral genomes that we start off just with a computer file to write a virus, not to make anyone sick, but to actually make them better. We programmed viruses to hunt down cancer cells. And now there's an entire field opening up for what we call vector engineering, because viruses are essentially the USB stick for loading programs into cells. So this field in general has been moving very quickly. I was also the co-founder of something called the Genome Project Right, as I mentioned in the introduction, which is really a growing community of scientists internationally that are thinking about, how do we start to write organisms from scratch? And what type of community do we need to do that? What type of safeguards do we need for that industry? What are the ethics of that industry? So it's really been a fascinating 2 decades.
For sure. So again, here's all you sort of need to know. This term, synthetic biology, is kind of this umbrella term that encompasses other technologies. And the purpose is to design or redesign organisms on a molecular level to have new purposes, to make those organisms adaptable to different environments or to give them different abilities. You know, Andrew and I like to say that viruses have kind of gotten a bad rap. We know that viruses are bad, but viruses are also just containers, and they can be used for good purposes too. And I think this is kind of an important point here because we're alive. We are living through a moment in time right now when, like it or not, science is at the forefront. We all got a crash course in human biology as soon as SARS-CoV-2 jumped and started spreading in other countries. And suddenly we had to remember what DNA meant and what messenger RNA was, and you know how the body works. One of the things that I observed during that time was, you know, we live inside of this container all day long, and we don't really know how it works. So part of what Andrew and I are trying to do here is to demystify how life works in a sense. And the community is trying to figure out on a very tiny scale, what are the effects, like how do the building blocks work? Can we engineer and figure out the minimum viable living organism? Because if we can start to figure these things out, we'll be able to exert more control over them. This doesn't necessarily mean that this work in science is incongruous with religion or spirituality. There's actually a lot of scientists who work in the field who are very religious. Francis Collins, who was the head of the NIH and has just become sort of a co-advisor to OSTP, you know, is very, very religious, has written a bunch of books, and is also in favor of using stem cells for research purposes. So if somewhere in the back of your mind you're thinking, this stuff feels a little bit like it doesn't mesh with what I think about the future, again, we would encourage you to keep an open mind. And it's more important to have that open mind right now because of some important things that are happening. SARS-CoV-2, the virus that causes COVID-19, acted as a catalyst for a lot of what we talk about in the book, for genetic sequencing, that's like figuring out what the code is, and synthesis, that's the printing part that Andrew was talking about. In effect, it kind of broke us free of our mental models for how to detect a pathogen, how to inoculate people, just how we think about some of this stuff. And that created this flywheel. And so there's been significant investment in lots of different places. There's some biotech veterans that raised $3 billion with a B dollars to create something called Altos Labs on the premise that fundamental machinery of living cells, it can be reprogrammed. And so there's a flood of capital being directed right now, and that's going to start to accelerate some of the developments. But again, we're on a very long horizon here. Excuse me. The other thing is that there are, you know, it seems like every day there are new and interesting developments. We aren't seeing a ton of products yet, but they are coming. We just had the Super Bowl, and Americans consumed 1.45 billion chicken wings. That is a lot of chicken, and like a unthinkable amount of chicken, and on one day. So that required like almost 750 million chickens who were grown on commercial farms, you know, which required hormones and antibiotics, and let's face it, not great for the chickens. So what if in the near future, instead of requiring hundreds of millions of chickens, instead we didn't need the commercial facilities. We had something that's called a bioreactor. It's just a metal version of a mother hen, where you would begin with stem cells, feed them with delicious amino acids, keep them nice and toasty, allow those cells to multiply, And eventually, without needing hormones or antibiotics, you get tender chicken meat, potentially from like a heritage chicken versus a commercial chicken that tastes like chicken. And it only took a couple weeks. It required a fraction of the amount of resources, and no chickens were harmed in the process. That's on our nearer term horizon. And already in Singapore, that type of chicken has gone on sale. It cleared regulatory hurdles, and portions were like $17 each. Now, that's a far cry from a 10-cent wing. But again, try to play this story forward. It just gives us interesting new options, and also potentially means that Miami, the city of Miami, could have a bioreactor for chicken wings downtown on like 3rd Street, and have all the delicious chicken you could possibly need without needing to rely on a cold chain or a global supply chain. So it helps some of the stability issues that we have today. Andrew, do you have any other interesting use cases you want to?
Well, I was just going to say, food has overtaken medicine in the investment in these technologies in the last year, which is fantastic. Medicine is number 2 because it's, again, so many diseases still have yet to be cured, let alone managed well. Or should actually put it the other way around, managed well, let alone cured. After that, it's materials. We forget how many biologically sourced materials are used to make the world around us. And again, if it takes 60 years to grow some of the trees like I have in my yard, that's a long time if you need more lumber. We're starting to get to the point where people are looking at how to make leathers, lumber, and other materials, just from these biologically sourced materials, and do it at any scale required. I particularly like the fact that we can start to distribute the manufacturing of these biomaterials to where we need them. And so you can reduce just a lot of the transportation costs of things like food and materials. So many different applications.
One of the things that we were hoping to do is to get you to imagine a future that is different from what you're currently thinking, because you're constrained by what you know today. So the center section of the book are all scenarios. So these are like short, speculative fiction pieces, but they're still rooted in data. So we didn't just go totally off the rails and make everything up. But they are 5 glimpses of how all this might turn out in the future. And there's different scenarios. Speaking of food, one of them is kind of an imagined best restaurants guide, that it's set in the year 2037. And so we make all kinds of recommendations for different parts of a city and where you would eat and how you would eat. But one of the scenarios that has been getting talked about a lot has to do with an experiment where people move kind of, sort of underground. And this came out of Andrew's incredible brain. Do you maybe want to give everybody an overview?
So apart from
especially because, so this is why I mentioned this, because of what Elon is doing in Miami, or trying to do in Miami.
Well, that's just it. In addition to loving biology, I love space. I was 6 years old watching the moon landing in front of a black and white TV. I have always loved space. And of course, we're in a new space race now, where space is becoming extremely cheap now that we can start to reuse rockets. So we're seeing space open up for commercial applications, and it's not just for nation states anymore, which means we have to get better at living fully sustainably in a closed system. They call it kind of circular systems. I think biology is going to be absolutely crucial for this. And the prototypes for living in these closed systems, like a space station or a colony, need to be made here on Earth. Like, there's just no other, you can't go and learn this in orbit. You're going to lose too many astronauts to experiments. So we have to prototype that here on Earth. So there's a scenario where this, essentially, there's a prize to develop a colony that can be closed, sealed, and sustain itself for 2 years with 100 people. And I think this is a real possibility in the future, and that it will lead to the development of systems that are truly sustainable, whether it's in food, water recycling, oxygen generation, etc. So this could be a big one. But the one I like the most is on reproduction, and start to choose your kids.
Yeah.
And maybe I'm going to hand this back to you, Amy.
Well, Andrew and I have, one of the things when we first met that we really, I think, or at least I loved hearing you talk about, was your ideas about fertility and specifically IVF. The book opens with our stories, our very personal, intimate stories of trying to start families. And, you know, in my case, I was pregnant 9 times. I have 1 child, and it was a pretty harrowing process. Over and over again, I was told by doctors, there's nothing wrong with you. And because there was, well, obviously there was something wrong. But because there was nothing technically wrong, IVF, in vitro fertilization at that point, was not really being suggested to me. Now, in hindsight, I know exactly what the problem was. I think there were some chromosomal abnormalities that just, you know, that was probably it. Now, if I had done elective IVF, if I had known that that was a real option, you know, if we had really explored that, then we could have created a whole bunch of embryos. We could have screened them and selected the ones that were, you know, most likely, given the data, to be carried full term. Today, I have, you know, I've got a daughter who's healthy and awesome. And we actually talk about this a lot. She's already planned on getting her eggs frozen. And I should mention, she's 11. So we are talking about these things now. She has a plan. We've talked about it. And I hope that she chooses IVF because it will solve some of the problems. We leave this very important thing, this precious thing, creating a family, up to happenstance and hope and chance. You know, my hope for her and for everybody is that we're all having plenty of sex in the future. We're having a great time and we're having a ton of sex. And when it comes to making babies, we're using science. And I know that, and also I hope that needs to be equitable and evenly distributed. So it shouldn't just be people who have the financial means to be able to choose that path, but everybody. And Andrew, I don't know if you want to mention, because we're sort of aligned on.
Oh yeah, so I have 2 kids. They're 7 and 4 now, but they're.
You haven't had the egg freezing conversation yet?
Haven't had to. Our challenges were completely different. You know, mine was rooted in the fact that I was never going to have kids, and so I got the taps turned off when I was quite young after having a lot of debates with doctors. And so it was more getting the systems rebooting. I could never quite get the sperm counts up again to have children. But I was like a kid in the candy store when it came to IVF. It was like, show me everything. And thankfully, it wasn't too much of a challenge for my wife. It was pretty straightforward. But now my kids go to the playground and they say, oh, I'm lab grown. And they explain, you know, insemination and IVF technologies to other kids. And so it's a little funny. But really, in all seriousness, you know, being able to control human reproduction as we've been doing and getting better at has delivered 8 million kids into the world that wouldn't otherwise have been born. And with the technologies that are coming online now, where we can start to make eggs and sperm in the lab and do much more sophisticated screening of the embryos that are resulting, it's really a game changer because we're moving into reproductive areas that we're pioneering. We've never been able to do this, whether it's 3-parent babies,
or
whether it's one-parent babies,
yeah.
You know, 8-parent babies, I'm sure will come into the future, or as one of the things that I have on my waypoint for the future, the first synthetic human genome that goes on to produce a baby. So I'm just keeping an eye on the time, Amy. Yep. We're at 4:30.
Yeah, so, or 7:30 yeah. We're on opposite coast.
Yeah.
So we have some questions that have come in. So shall we get Christina? To the Q&A portion? And if you haven't yet had a chance to submit your questions, you can use the feature at the bottom of your screen to do that. We're happy to answer whatever you'd like to ask.
Okay, here we go. So How would this technology be applied to benefit the elderly? Could you just reverse aging or cure diseases like Parkinson's?
Oh, that's a great question. One of the researchers that I work with that I really just admire is the Harvard geneticist George Church, and I've had a number of conversations with him on this. But first of all, there's two sides to the aging challenge. One is of course we're all naturally aging. That's kind of built into our genetic program. We don't know how to slow that down yet in a way that's may not cause another problem. So if you're 30 years old and you start taking a medicine that you think is going to help you live longer, you're only going to find out in 50 or 60 or 70 years. So the reversal of aging is a serious area of R&D where you can get measurable results very quickly. This is happening mostly in animal research today, typically with companion dogs. These are not research dogs. These are like your dog at home that's getting old. And the work there is essentially to reverse some of the aging effects that we're seeing in these animals. I'd love to see that research get a lot more funding because so many of our human diseases are really just from the aging process. And if we can start to address those and essentially slow that process down or rewind it, we're all going to age a lot more gracefully. So early days, but one of the most exciting areas of R&D, one of the most accessible ones. A lot of people think about it and want it, and we've got the perfect animal research population to really do the work with our companion dogs.
This is something that we cover in detail in the book, and again, we've tried to explain this in pretty plain language, but we talk about what causes cellular aging and some approaches and some research that's being done to either stop or reverse that process. I think in an ideal future world, we live long lives, very long lives, and we are healthy up until the very, very end. And the very, very end is a fast process. So if we can reframe aging as a pathology to be treated versus a long, inevitable decline, then I think that's terrific. But we also have to think about knock-on effects. So if we have populations that are living much, much longer, that starts to change the dynamics of family-run businesses, of term limits, people who are serving lifetime appointments for some political appointments, tenured professors, could be tenured for 80 years and literally never change their syllabus once. So we do need to think through what that would mean, because it also has to do with our social safety nets and making sure that not only are we living longer, healthier lives, but that the quality of life is good too.
So are we then playing God a little bit? Like, can you talk a little more about the spiritual or religious aspects or moral aspects?
I can start. First of all, I would like to acknowledge that a lot of times when you hear people talk about scientific research, unfortunately, or people are asking questions, unfortunately, I think they kind of brush off that question. And I think there's been a lot of people who won't have it. Like as soon as somebody mentions their religion or spirituality, it's like the end of the conversation, which I think is wrong. I think we need to create space because we all have different beliefs and we're all sharing the planet. We need to come together and be able to talk about some of these things. And I think there has been probably too much discounting of people who feel religious, who are religious, and they feel like they can't participate in some of these conversations. So I just want to say that to start with. Now, you could ask the question, if the technology exists to improve lives, to do genetic surgery on an embryo in advance, basically like tweaking and fixing things. You know, if we have technology available, do we have a moral obligation to use it? The challenge here comes with some of this work it would enable us to make decisions about future generations. It also probably means that there would be embryos that would not be used and either have to be banked in perpetuity or would be discarded. And I know that that's going to be a challenge for a lot of people because some communities believe that life begins at the moment that the material comes together and an embryo is formed. So that's not going to be easily resolved. But just because that's a hard conversation to have doesn't mean it's okay for us to go away to our separate camps and continue to yell at each other. We're going to have to figure out a way around this, because another thing there's a couple of other stories related to me and my family in the book. You know, my mom, today would have been my mom's birthday. She died many years ago of a pretty horrible, rare cancer that at the time there was no cure for. And so the only treatment was a cocktail of pretty heavy duty chemotherapies. And, you know, it was awful. Now, today there is research underway that would have helped what she had, and probably, if not extended her life, could have eradicated basically what she had. That involves research on existing stem cell lines and potentially new stem cell lines. So we have to ask the question, you know, how are we going to prioritize who we're helping? And we can't be dismissive, because if we're dismissive, then we're going to miss out on these opportunities, which I think would be a real shame. Andrew, do you have anything that you want to add there?
The thing that I try and keep in mind, I was raised Catholic, but the thing that I find really interesting is that all life is the same at a molecular level. The processes of life, whether you're talking about a bacterium or a banana or a blue whale or you and me, it's the same mechanism. So I just look at it as a universal programming language. I'm sure someone that's more religious would say, oh, it's God's programming language. I like the idea that we're learning how to read that code and understand it and start to create with it. And if that's playing God, you know, it is what it is. I just look at it as learning how to program life. I have got no interest in modifying the core mechanisms of life. I don't want to change the processor, so to speak, but I do really like the idea of being able to program living organisms to reduce suffering, to help us grow and thrive, and continue to grow and explore our knowledge and understanding of our planet and the universe.
It's worth noting that every time there's a new scientific development in the life sciences or biotech space, we immediately, all of us, reference the scary science fiction movies or books that we've read. And storytelling, you know, we are creatures of habit, and the stories, especially when they're really effective, like your Jurassic Parks of the world, Frankenstein, it's hard to unhook from those. So what we would urge you to do, and what we've tried to do in this book, is to present different ideas about the future, because, you know, if we can all agree that we're not in Elon Musk's simulation, and if we still have free will, then what that implies is that we can choose which future direction we want to head in. And it doesn't have to be a dystopian hellscape. It can be better than we have today, better than we can even imagine today. But that future is going to require planning and conversation and curbing some misinformation spread and some other things that we outline at the end of the book, where we have some solutions and suggestions for how we can make sure that this incredible science benefits everybody.
I think you have to bring the Dalai Lama on board. He is such a proponent of science, and of course, you know, alleviating human suffering would be right up his alley.
Yeah, I'm not preaching to the Dalai Lama. I'll tell you, I had an interesting experience. Andrew, I haven't had a chance to talk to you about this yet. I was on a show called Coast to Coast, which airs coast to coast from 1 a.m. to 5 a.m. And it's an AM radio show. And perhaps some of you are listeners. I'm really glad that I was on the program because it gave me an opportunity to hear the thoughts and concerns that people are having and the real fears that they're having. And I worry that, again, a lot of the questions that I got had to do with COVID, which the book is not about. But I think the questions are coming from a place of genuine concern. And we kind of have to make ourselves available to answer questions in a way that's not immediately off-putting or like political or, incendiary. And I just feel like we kind of got away from having civil conversations. So what I would much prefer is that everybody who's a doubter, I'd love the opportunity to change your mind. I'd love the opportunity, honestly, for you to just hear us out and to keep an open mind and to totally we welcome disagreement as long as you don't say, as long as the trust fall happens with us at the beginning, the moment you crack open the book, not at the end. And if I just think that I don't know, I would much rather reach that group who I think needs to hear what we have to say.
Where is the majority of this work happening? Who is funding? Is it private? And who regulates this research right now?
This is a global field. Just about every country in the world is starting to explore this technology. The leaders are the US, China, Europe, but I work with groups in Africa. The student organizations that are really training the next generation of scientists are global, and more of the R&D is being done outside of academia in startup companies. So it's very entrepreneurial. The closest industry that I've ever seen to kind of what I'm seeing in synthetic biology is just computing. And we saw at the beginning of the early days of computing, it was only accessible to very elite groups. And of course, 3-year-olds are playing with our computers today, and younger. But my daughter's 6. She's learned programming for the last year and a half. So right now it's a little harder to get started in synthetic biology than with a computer system. But we're starting to see the infrastructure to come in place that I expect within 10 years we'll have 8-year-olds starting to learn how to do the basic programming. For example, make a cell start to glow or blink. So it's really a global field, and it's moving quickly. In terms of regulation, it's a hodgepodge. In the U.S., we have the CDC, we have the FDA, we have the USDA. There's so many different organizations that kind of touch the process. There's no cohesion, and this definitely needs to be reviewed and upgraded and hardened as we start to make this genetic engineering technology, more easier and faster.
2 threads to tease out. First is some of the companies that are involved in this space, would be shocking because you don't expect it. So Microsoft, believe it or not, is actually a pretty big player in this space. They are working on bunch of things from precision agriculture to figuring out how to use DNA as a hard drive, as a storage device. There are investments and lots of research being done in this space by Google.
Massive, yeah.
Yep. So when I was working on my last book, The Big Nine, which is about the future of AI, one of the things that I kept coming around to over and over again was some of the same companies and the people like the venture capitalists who are very heavily involved in AI are also very involved in synthetic biology. And it's interesting, and that makes sense. Advancements in AI will help the field of synbio advance as well. But it's some unusual players. So that's the first thing. The second thing I want to pick up on is kids. So Andrew and I are obviously pretty passionate about our kids and passionate about education, in particular in this space. So there is a hidden Easter egg in this book. At the very end of the book is a QR code, which I promise you does not send any malware. It goes to a link to a Dropbox folder. And in that folder, we've put some videos, some TED Talks. We just curated a whole bunch of stuff because there are opportunities for kids to start learning, what this is. This is going to be a field that by the time our kids are entering the workforce is going to be in high demand. They're going to need people. So we stacked in that folder a ton of resources and ways for kids to get involved and all kinds of goodies.
Fabulous. Can you talk a little bit about your collaboration on the book and how you worked together and what your research was like?
Yeah. Well, I drove Andrew crazy, I think is a lot of how this worked.
I gotta say, you drove. That this is not Amy's first book, so it is my first book.
It was Andrew's first book. It was my first time writing with another person, and Andrew's awesome. He keeps talking. He says he's got these squirrels in his head and they're squirreling around. Andrew's got like 100,000 amazing thoughts a minute, and so maybe there's a faster animal than a squirrel. I don't know.
No, squirrels are amazing.
Hummingbird.
Yeah, no, I'd take squirrels any day.
Yeah, so I mean, it was a matter of I had started working on the book, and then I was like, I think I need somebody else who's got more of a science background to like partner up on this one and help me explore. So that's kind of how it started, and I think the end product is kind of speaks for itself. But it was fun, super fun working with Andrew, even though we were far apart.
Yeah, we only met after the book had been written. So
in person. Yeah. But
so,
Zoom and phone calls and texts and
But it's absolutely easy working with Amy.
Okay, let me see if there's anything else. Someone would like to know, if you could get any genetic enhancement, what would you get or do?
Oh, I got a list of a few of them. Personally, I want my eyes to be completely re-engineered. I'd like to be able to see night vision, etc. But one of the ones that's always at the top of my list, if there was an off switch for children, take the narcolepsy gene, put some controls in, I would just love to be able to just touch a spot and have them go to sleep. Yeah. That's a big one for me.
Let's see. I am lactose intolerant and I love cheese. So I wish there was a way to do some genetic surgery so that I didn't have to pop a bunch of medication every time I wanted to indulge. I think that's potentially sometime in the near future, something that could happen. So that's my like practical answer. My fantasy answer is I would love to get some form of internal Adderall that I could flip a switch on myself and go into hyper productive zone with no ill effects afterwards. So I'd love to be able to turn my productivity on and off without medication.
No, there's some of the ones that people have mentioned to me over the years. They want to be able to grow their hair again. They want to be able to turn off hair growth. They'd love to be able to just, again, longevity is a big one. That's one of the reasons why it attracts so much investment.
Yeah.
Is because people really don't want to have all the diseases of aging if possible.
Yeah.
And I think go ahead.
I was going to say, Alto's raising $3 billion. I don't know what the valuation was. I mean, that's a staggering amount of money.
That was a seed round.
Was that?
That was a $3 billion seed round.
Yeah.
Which is unheard of.
Which is great. So that's exciting. And it's about anti-aging, right? So that's exciting. It's also problematic because in the mid 80s, we went through something called an AI winter when a whole bunch of promises were made and a ton of money was thrown at companies, and when the products didn't materialize, people, got upset and kind of left, and here we are today. So I'm just hoping that everybody exercises patience on this one, because there's a lot on the horizon, but we've got to be willing to exercise patience and let things develop.
I think that's a good question. Just how long do you see this taking? Like, how many years are we going to be waiting?
It's our favorite question we get.
Mm-hmm.
And certainly it's already, so genetic engineering has been around since the 1970s. And again, like your laundry detergent is filled with genetically engineered enzymes. We already have many different medicines on the market that have been made using genetic engineering technology. The thing that we're seeing is now that it's digital, it can be done faster, better, cheaper, which is opening it up to a broader range of programmers and engineers, and we're starting to see things come faster. So enzyme engineering today is accelerating like crazy. And this is any protein, actually. So it could be a structural protein. Imagine synthetic woods, for example. It could be, but it could also be a catalytic process. I work with I don't work with them directly, but I've been connecting them with different groups around the world, with a professor that makes an enzyme that degrades plastic. And so they found it naturally in bacteria that were growing in garbage dumps, literally using some of the plastic as a possible food source. But they took the code for that enzyme, and they've been engineering that enzyme to work faster. And now they're working with groups like Google DeepMind to accelerate it even faster using AI technology. So one day, styrofoam and plastics can just be gone.
It's fantastic. I mean, there's so many wonderful benefits that can
medicines, foods, materials are the big ones, but the sky's the limit. Anything that biology makes.
The scary part is who controls it, and how, is there a dark side, and, do those things enter into it? Can we use it for the common good, for the global good?
Go ahead.
Go ahead. Well, in general, nature is natural. Life systems are natural. Anything made by a living system can be broken down by another living system. The biggest risk in the short term, at least the one that I've really gone on and talked with a lot of people about and done everything I can, is the virus problem, because viruses have very small genomes, and of course we've seen how they can create a pandemic and change the world, just with COVID. So COVID has probably been, in my opinion, an accelerator of better biodefenses that we may not have seen until something like this existed. And frankly, we dodged a bullet. As far as bad as it's been, I think there's been about 6 million deaths globally. That's a small fraction of what we saw 100 years ago with the 1918 influenza.
Mm-hmm.
So again, I think the important thing to bear in mind, because we get asked this question constantly. So how soon? And the answer is, we don't know. And that's okay, because we're talking about basic research, which means fundamentally altering how we currently do things and think about things. This is the kind of stuff that takes a really long time. So we need to be able to exercise some patience. We also need to be aware that, as with every technology and every science that has ever been invented, there was always the possibility of misuse or intentional, either intentional or accidental misuse.
Mm-hmm.
So, and that is certainly true when it comes to biology. But just because the possibility is there doesn't mean we ought to shut it down and stop doing any research or looking into it. One of the very last chapter of the book begins in Asilomar, California, where after another huge, important scientific discovery a couple of decades ago, some scientists got together in a room to discuss whether, what should we do?
Oh, longer than this, Amy. It was the 1970s.
Well, it's a couple decades ago.
Oh, it was more than a couple. That's at the genesis
I
of
was
the
born
field.
in the 70s, so we're going to stick with a couple decades. It actually happened like right before I was born. At any rate, my point is that we should not start the conversation with no. We should lean into uncertainty about safety with curiosity, and with the intent to do everything we can to create safeguards and guardrails. So it's going to have to be a different approach going forward. And for some people, that is going to be difficult, but it is absolutely necessary, because if not, all the amazing stuff you just heard Andrew talk about is never going to happen. And in addition to it being inspirational and exciting, it's also going to be necessary. We are not going to solve the problems that we've created that are going to challenge how we live on this planet alone. We're going to have to figure out some other ways. So it's time that we strap in, allow ourselves to be open to alternative ideas about the future, to challenge our cherished beliefs, and to plan, to intentionally build something better.
I want to just add one point to that, Amy, which is great. It's the engineering of cellular systems can happen a lot faster than most people realize. Now, with humans, we tend to be very conservative because we don't want to cause harm. First, do no harm is kind of the working with humans. But working with bacteria, working with cells, working with these microbes, things can go very quickly. The Moore's law, of course, with digital technologies moves very quickly. The world is powered by electronics today, even though the first transistor was only brought to market in the 1950s. The difference here is cells are the most complex factories on the planet today, and they make every living thing just by changing the code. So the evolution of synthetic biology is actually rate limited by how quickly we get to write programs. In other words, it's rate limited by software, not the physical hardware, so to speak. And that's a game changer. It's going to take us a while to figure out how to program cells and do it well and do it quickly, but then it'll accelerate faster than most people realize, because we will get very good at writing it, or our software tools, our AI-based software tools, will learn collectively from all of our experience.
So exciting, so exciting, so insightful. Thank you so much for your work, for this book, for tonight's presentation, which I think has been truly just fascinating. It was so well explained. So thank you to everyone watching for your questions and for being with us tonight. Just a reminder, you can buy the book at any Books and Books location. If you're in Miami, come by and see us. If you want to buy it tonight, just click on this green button and it'll take you there. And I just want to say thank you again. I love that, like, I'm lab grown. I love the story about your kids being lab grown. And happy birthday to your mom, Amy.
Thank you.
Just lovely that it's today. So thank you both. And we will see you the next time, I hope.
Thank you very much for hosting us. We really appreciate it.
Thank you for supporting Books and Books. Thank you. And thank you for being here. Okay, good night, everyone.
Good night.
Good night.